Today, so I would like your undivided attention.
Hi, my name is Mohammed Abouelsoud. You guys can call me Mo. I am the CEO at Unimind Company. We develop neuromodulation devices for Alzheimer's disease and Parkinson's disease. I was a student at the Ohio State University. I was studying physics and neuroscience, and we do a lot of exciting work with electrical stimulation in the brain. And so Mrs. Nerlich invited me to speak about different ways to look at the brain, how the brain organizes together, and discussing new advanced concepts in biological structure and biological function as a whole. I want to play the video for them. And just for everybody's awareness, this is a prototype of the device that goes in the brain like that. And we have these electrode nodes that send pulses down specific tracts of the brain to activate or inhibit regions of the brain. So here's an example. Everybody know Parkinson's disease? The disease, the tremor disease, Muhammad Ali, Michael J. Fox? Okay, I guess we can, let me restart it real quick. So this is a patient, 76-year-old woman with a resting tremor in the right hand. This is prior to using our device. She's had this for 7 years. This is 5 days after using the device. What? Whoa, this is very exciting. And the exciting part here is 3 weeks later, she stopped the device. 3 weeks later, her tremor is still diminished. All right? So we saw an 80% reduction in the tremor. This is very exciting work. We're stationed out here in Cleveland, Ohio. And we are excited about the future. How do I get back to the presentation? So we've done work with Alzheimer's disease, done work with Parkinson's disease. So this is going to be very more mainstream for the following years ahead. All right, everybody ready to go? So I heard this is an hour, 20-minute class. So I created a special presentation. We have a little break in the middle. We're gonna have the first half of the presentation and the second half is very AP oriented. So it'll be very fun, okay? Good. So we're going to first talk about this, something called the constructional law. This is a law of physics that governs how any living system grows. Tree, plants, human brain, lungs, rivers, how dynamical systems flow, rivers through a mountain. As you guys all see, they're structured very similarly. Here are the veins and the arteries in the lungs. These are the neurons and the synapses inside the brain. River flowing through a valley, mountain, and a tree. All of them have that very similar structure, where we have a large central trunk, and it branches off into these distinct fractal patterns. Everybody see it? The lungs, the trees, and the river, the large canyon of the river. The reason why this happens is because every dynamical system deforms its shape such that what it's flowing through can flow through it more efficiently. So we have one system A is flowing through system B, and system B is flowing back through system A. They're talking to each other. So system A changes its shape such that system B can flow through it more efficiently, so to speak. This is due to energy conservation principles, where we want to choose that path of least resistance of flow, but this is not an electrical circuit, it's more of a larger mass system. So this is how larger mass systems flow more efficiently. Now, why is this important? Why am I bringing this up? The reason being is because the brain, in your brain, everybody here is 17 to 18 years old, right? Your brains, over the next 10 years, 25 to 28, are going to evolve very much like this trunk, very much like this tree, where we have this branching effect. So even though all the neurons in your brain are going to stay similar over the course, the structure is going to stay similar over the next 28 years, or the next 10 years, what's going to happen is that the connectivity between these different nodes on the tree are going to heighten or non-heighten. The brain and trees and these rivers evolve on a mathematical principle called S-curves, where we have phase transition at certain plateaus that reach certain plateaus prior to increasing onto the next threshold. So what does this mean? Everybody see this S? So I usually give this presentation to like a motivational presentation to economic classes or psychology classes. But from a biological perspective or a physiological perspective, what's happening is that in the brain, we have these points inside the brain, these regions that are becoming more highly connected to other regions over time. And it occurs on these plateaus. So right now, as everybody here is 17, 18, you're in the midst of the development of the first layer of connectivity, that first trunk of the tree of your brain. When the time you enter university, 20, 21, you're graduating university, you're going to be entering that next threshold of connectivity in your brain. So you want to make sure that the connections you develop now, and I know this is a great AP class, are strong and well rooted such that when you reach that next curve, that next ramp up, it starts from a high base. Okay, you don't want bad connections now and good connection later. You want good and good. Okay? Who here, outside of this classroom or in this classroom, have heard the concept of a brain as a computer? Brain as a computer. Do you guys think a brain is a computer? No. Who said that? No, it's not a computer. And it's not. Neuroscientists nowadays are saying, well, the brain is actually like a tree. It processes information like a tree. It grows its roots like a tree. And it dances with the wind very similar to a tree. So the idea that the brain is rooted and has a fixed structure like this computer and you have to type on it with 1 to 0 is long gone. The new theory is that the brain is moving, it's dynamical, it's changing, it needs to be nourished, watered. Okay? Your brain is a tree, it's not a computer. And the reason why this is important is because of a concept called neuroplasticity. Who here has heard of this concept? Have people here taken EP psychology? So what is neuroplasticity?
It's like the ability of the brain to change based on different concepts.
That's correct. The brain can change, and the brain adapts itself. It adapts its structure and its function to flow more efficiently to what it's looking at. So, this has two effects, a good one and a bad one. So a good one, if you train your brain to wake up early every day, exercise, study every single day, do the homework, prepare for the future, your brain is going to structure and be efficient towards that area. Now what if you watch TikTok all day, wake up late, you don't make your bed first thing in the morning, right? Over time, your brain is going to build those bad connections along that curve and just be more efficient in that direction, all right? As everybody here is 17, 18-year-old right now, your brains are in the highest, most maximum state of change. My brain's 24, so my brain is less able to change as compared to your brains, okay? So this is a very, very important concept. The brain can change. Now, everybody ready? There are many ways in which the brain could change. Many, many different ways in which the brain can change. There are 4 major categories here, and we're gonna have 3 activities in this presentation today. We're gonna have our first one right now, okay? Well, in 2 minutes. But the first one is called homologous area adaptation. So, sometimes, as you guys know, the brain is symmetric, right? There's symmetry. There's functions on this side, and it's mapped to the mirror on the other side. This is not anatomy, but who has taken anatomy? Generally most, okay. So what is that region of the brain that connects both hemispheres together? Who remembers? Corpus callosum, great. So sometimes there are abnormalities in the gray and white matter structures of the corpus callosum. And the ability for one side of the brain to talk to the other side of the brain is inhibited. They're not able to talk to each other well. All right? But the functions of the brain need to communicate with each other. Left side of the brain associated with language, thinking, making words, writing. Right side of the brain is more intuitive, absorbing information on a global scale. When these two regions or these two hemispheres of the brain are severed, patients need to undergo a rewiring process, this neuroplasticity process, of being able to adopt functions of language and writing and learning on the other side of the brain, and vice versa. So for example, if you have a patient that, and this is a stretched example, but this is how it goes. The truth is that this happens much more on a millimeter level, and the functions are much more specific. But let's say you have a patient that lost the ability to move their pinky, right? They're not able to move their pinky. There's a study on this on monkeys. Lost the ability to move their pinky. What they did is they saw the motor cortex, they saw the region of the brain associated with pinky movement. And let's call this the thumb movement. So they have this again. So they have the region of the brain. So this is the region inside the motor cortex. This is the pinky and this is the thumb area, right? And what happened over time is since this region was severed, this region grew and took over the area. So now it just became one large thumb area. All right? Okay? So this is one type of neuroplasticity. So this is a type of neuroplasticity, the second time, called cross-modal reassignment. This is when two regions of the brain that are distinct become very intercorrelated with each other. All right? So region A becomes more integrated with region B. So, a very perfect example of this is when you start learning playing music. Who here plays an instrument? So what instrument do you play? Viola. So when you first started playing the viola, you were still training yourself, how do I hold the viola? How do I make the notes with my fingers? How do I hold the bow? How do I do it synchronized, you know? So the two regions of the brain, the motor region, and the region associated with listening to music and sight reading, so three regions, right, are trying to become more integrated with each other. How do we do this? Then over time, there is the ability for these regions to connect with each other, and you're like, oh, and then you can swiftly, those brain regions are able to swiftly talk with each other. All right? So this is another form of neuroplasticity. There is one form of neuroplasticity that I want everyone here to remember, but it's not this one. It's something else. Okay, here's our activity. This is the fun one. So we have something called compensatory masquerade. This happens a lot with patients that suffer from distinct brain injuries. So let's say you have a big region A. So region A of the brain. Okay? Big region A. Then you have inside that region a sub-region called sub-A. All right? And let's say sub-A broke. Demyelination, brain trauma, it's not working anymore. This type of neuroplasticity says, well, A can still work because it can find a new pathway jumping around sub-region A. So do you guys want to test this concept? Let's test this concept. Okay, everybody come up and place your hands on this table. Or this table right there, or that table right there. So place your hands on the table, one hand on the table. Okie dokie. All right, everybody close their eyes. All right, now go back to your desk. With your eyes closed. Maybe slowly. All right.
I know.
Good. So, yes, everything okay? So, do you guys see that connection? You have a big region, the region, which is find the desk. And then you have a sub-region, eyes open to look where your desk is. It's shut down. But your brain adapted itself to re-find a new connection to be able to get back to the desk. Does this make sense? Cool, fun? All right. This is the important one. This is the one I want you to remember. The last type of neuroplasticity called map expansion. The reason why I want you to remember this neuroplasticity is because it underlines all of them. Everything that we just spoke about, this is basically the basic. So map expansion is very simple. You use a region, that region becomes larger, quote unquote, becomes more interconnected. Very easy. When you're playing viola, or when you're playing an instrument, playing a sport, that region becomes more interconnected with the daily thinking of your schedule, of your day-to-day habits. When I was in high school, we had a lot of athletes, so I wrestled and football players. That region of dexterity and being able to move and be on your feet and their visual spatial awareness is so magnified and interconnected with the brain that they're very naturally twirling their thumbs and twirling a pencil in their hair in the habit, moving their legs around, just jumpy and jittery, right? They're ready to move. The part of their brain that's associated with movement, athleticism, and being able to control your body mechanics is large such that it's integrated into all of your day-to-day functions. Okay? Map expansion. This is the number one I want you to remember. Reason why map expansion is important is because when this region is large, the probability for it to connect to other regions also increases, is high. Okay? All right. So this is the first principle that I want everybody to remember. Our brains are trees. They're not computers. Okay? All right. So since everybody here took AP anatomy, well, anatomy in general, right? Most of the students here? Okay. Everybody knows about the regions of the brain though, right? Different types of regions of the brain associated. So you have to ask the question. I have a region right here in this hand, right? And then I have a region right there in this hand. So two regions, boom, boom. How do they talk to each other? A lot of times that we don't really show this in lectures or show this in presentations, which is the way that they talk to each other is through tracks, neuronal tracks inside the brain. They cross a bridge inside the brain. They cross these bridges to talk to each other. Okay? So the term for this is neuronal tracks, or the imaging is called tractography. There are three major types of tracks inside the brain: association tracks, projection tracks, and commissural tracks. Association tracks are the ones up above that you see here, which are associated with connecting regions of the brain along the same hemisphere, back and forth, sending information from the visual lobe up to the frontal lobe and motor cortex to process what you see. Projection tracks, projection fibers, connect the entire brain to the spine. All right? They go from the spine to send information to higher regions of the cortex. And then commissural tracks are crossing that corpus callosum. All right? Crossing and having the hemispheres talk to each other. Okay? Now, we're going to play another activity. It's going to be another fun game. And this one's seated. Okay. So, everybody remember, the brain regions, the regions of the brain talk to each other with tracks. All right? Good. Something very important that I want everybody here to remember is that because we have many brain regions and they talk to each other in tracks, those brain regions are not isolated. They don't activate on their own. They activate in networks. Okay? When you have a tree and the tree is dancing in the wind, is only one leaf dancing or is the whole tree dancing and swaying? The whole tree is dancing and swaying. It's not just one leaf. Same thing with the brain. The brain dances and sways in many ways. There are three major ways that we're going to talk about today. The first one, this is the first way. The first network, major network, is called the default mode network. This is the resting brain. The relaxing brain. The brain that's on default mode. All right? This is the brain when it's not processing information in the outside environment. It consists of many, many areas, but the three major areas are medial prefrontal cortex, the posterior cingulate, and the angular gyrus. So, the way to remember these regions, or to remember this, is does everybody here know about the hippocampus? Region of the brain called the hippocampus? Yeah? Yeah. So the hippocampus lies in the center of the brain, a little bit central of the brain. It intervenes with, it sends fibers out to all of these regions like a tree. So if you think about the hippocampus is like the trunk of the tree right before it spreads its branches, right? And so when individuals or people are relaxing and they're chilling and they're just like going to that default mode, the hippocampus is sending information and replaying old visual memories. Something important I want to note for everybody here is, everyone here has learned that the hippocampus is associated with memory, right? This is correct. What's deeper is that the hippocampus is associated with memory mapping, not just memory. The memories are not stored in the hippocampus, they're stored in the whole brain. All right? The hippocampus just maps where they are in the brain. Okay, this memory is there. Oh, I'm going to send this memory there. So this memory is over there. All right? So these visual memories, these memories that are replaying the past when you're relaxing, are intervened in the posterior cingulate right behind the visual cortex. Okay? So everybody show me your default mode relaxing face, because we're going to test this later. I'm just chilling. Okay? All right. Because we're going to run through them later. We're going to play a game. Now we have our next major network. This is called the dorsal attentional network. This is the focus brain with sustained attention. Note here the sustained attention. Why is this important? Sustained attention means you're looking and your eyes are not moving. E, F, P, T, O, C, L, E, E, D. Let's focus. So this sustained attention brain, is turned on when you're taking a test, you're focusing on questions, you're studying, you're playing a game. Who here plays football? Football, your alignment, you're focused on the player ahead of you, or you're focused on the path ahead of you to catch the ball or quarterback. All right? The regions of the brain associated with the dorsal attentional network are the interparietal sulcus and the frontal eye fields. The way to remember it is like this, because these are the words, but I want you to remember the concept, the emotion behind this. When the eyes are fixed, my eyes are not moving, they're fixed right now. I have a region of the brain telling my eye fields to stand still, focus. That's the interparietal sulcus. My interparietal sulcus is telling my frontal eye fields so you stand still. All right, and stay focused. Everybody show me your dorsal attention network. Show me your focus brain. Look. You can stay in attention, look at me. Okay, show me your default mode brain. Dorsal attention. Okay, good. And let's do the last network here. This is called the salience network. This is the selecting brain. This is when your brain is choosing what to focus on. This network, it lies in the middle between the transition of the default mode network and the dorsal attention network. So it's like a transitionary state brain. So, who here has heard of the amygdala? You heard of the amygdala? What does the amygdala do?
Control like basic functions.
It does control basic functions, so this doesn't not control. That's the correct answer. But there's something very, four-letter word, big concept with the amygdala, big emotion with the amygdala. Fear, which is a basic function. So this is correct, so this is not incorrect. Fear, amygdala activated your fear. Ah! Okay? Your brain is constantly searching about items in the environment to be scared of or to be attentive towards. The insula is associated with that, associated with reward centers, associated with being attentive towards something. Is this thing going to scare me, or is it I'm going to be happy about this thing? What should I do? Right? It's constantly searching. So this region of the brain is, let's say, it's activated when you are in a new location, let's say a new museum, new house, new stadium, right? You're selecting, just getting to know the environment, or you're meeting new people, meeting a new group of people. Just, am I gonna like this person? Does this person look scary? Everybody show me your salience network. Okay. Default mode network. Dorsal attention network. Show me your dorsal attention network. Default mode. Salience. Okay. Good. Fine. The important concept I want everybody to remember, because there's many different types. There are hundreds of networks, but these are like three major ones. Right? The important concept I want everybody to know is that the brain operates with networks and they're connected with tracks. So, I was talking about regions, dorsal region, frontal eye fields. I wasn't talking about tracks. And the reason being is because this is such new science that the science hasn't been updated yet. Literally, as of 2021. So let's look at this region. So we have a region here, regions of the anterior cingulate and the amygdala. All right? Let's do the top of the brain and let's say the middle side of the brain, right? Let's look at this one. Which one of these is going to connect the top to the center? Make a map in your eyes. How do I get from the top of the brain to the side of the brain? Which tracks do I need to follow? I need to follow this orange one, right? I need to go down the orange one, and then I need to move along this purple one. All right? The corticospinal tract, the enunciate fasciculus. Arcuate fasciculus, excuse me, the enunciate is the retina. But the way for the amygdala regions to connect to these higher anterior cingulate cortex centers is through by moving along the purple, then up the orange, and radiating through the orange fibers. Does that make sense? So we have regions, cities, and then I have maps, highways, how to connect the two cities together. Okay? Principle 2, the brain operates with networks and tracks, not regions. All right, so we're gonna have a fun game. I wish I played this game with the last class. I came a little bit late today. I'm from Mayfield Heights, Orange High School. Solon, Sugar Falls, you know Sugar Falls? So this is where I'm from. So when I I casually got into my car this morning, 7 a.m. I said, okay, let's get to Highland Heights. Because I thought it was going to be like down the street, 20 minutes. This is 40 minutes away from Sugar Falls. Oh my gosh. What? I was like driving in the countryside. I was like, what is this place? Very fun place. Okay? All right. So who here took AP Psych again? AP Psych, so good majority. But who here knows about concept of psychology and the brain and all this stuff? Okay. So we know this word. Have we heard of this word before? Consciousness. Who here can give me a super duper simple definition of consciousness? Few words, less than a sentence.
Being aware.
Awareness. Being aware. Awareness. Good. So this is something very, so what's your name?
Gavin.
Devin?
Gavin.
Gavin. Okay. So Gavin. Where in the brain is Gavin? So is Gavin in this region? Is it just this tract, the tract that goes up the brain down the spine? Is it 2 tract? 3? How many regions do we need to remove from Gavin's brain till Gavin becomes not Gavin? What? How about Mo's brain? How many regions do we need to remove from Mo's brain till I just become, who am I again? Not Mo. So everybody here has heard of Alzheimer's disease, right? So Alzheimer's disease is sometimes these patients, who am I? They forget who they are, they forget their mom, their daughters, their sons and grandchildren. Who are these people? Why are they talking to me? So these disorders of consciousness, these diseases of consciousness, is when there's large networks effects is degenerated in the brain. But the purpose here that I want to talk about today is there are many, many, many ways in which the brain becomes aware. Okay? And we're going to go through them today, and then we're going to have a really fun activity at the end. Okay? And when does this class end?
10:40.
42. So, all right. Let's go to the first one. First one, called higher order theories. The important concept here is that the brain operates in hierarchies, like a building. Floor 1, floor 2, floor 3, basement, top floor, top of the building. So, who here could guess what is the highest floor of the human brain? The top floor of the human brain that makes our human brain distinct from monkeys and reptiles and all that.
Frontal cortex.
Yeah? Yes. Frontal cortex. That's the highest floor. What is this lower floor here? The base of the brain.
Or like autonomic functions.
That's correct. That's correct. It controls the autonomic function. It is the cerebellum. It's the brain stem, the cerebellum. Okay. The hindbrain, sure. So more importantly, I name it as the brainstem here for this purpose, for this class. The brainstem. The brainstem connects to those reptilian functions, just breathing and temperature, and sweat, hormones, right? And then we have the layer right above it, which is the emotional centers, amygdala, insular cortex, hippocampus, and the highest human regions, the neocortex. It's called frontal lobe, areas in the motor cortex, visual lobe, right? But as you can see here, the brain grows and turns on in these layers. Layer 1, like a building, right? Times up the left. So, for example, playing football, all right? Or let's say when you're shaking somebody's hand. First, you have signals coming into your hand, playing football, about to get tackled, and then it goes up the nerves along your body, into the spine, up to the brainstem. Then it controls the emotional centers. Oh, this hurts. I don't want to be tackled. Goes to the frontal lobe. Oh, I need to make a decision right now. I cannot be tackled. So I have to move my body around to stand up straight and to run forward so I can dodge the opponent. All right? So signals came from the body up into a tree up to the highest nerves. So this is how the awareness comes. So Gavin is first body, then higher emotion, then Gavin is up is awareness of the body. And the body has emotion. Okay. This is good, the hierarchies of the group. So that's the first theories of awareness. What is the second theory of awareness? The second theory of awareness is if as though the brain is like a balloon. In and out, in and out. That these signals are moving around to each other very like a wave in an ocean. All right? And this one is, by the way, and the way I structure this, number one is the most outdated theory, so the oldest, and then this fourth one is the newest. So each one gets newer and newer. All right? So as you can tell, this one is floors. Next one is, okay, the floors are talking to each other with telephones. And, all right? Like a balloon. So when you have regions of the amygdala and the fear response center, the fear response center, so I'm the amygdala right here. Okay, let's play a game. Let's see if they test the structure of the brain. I'm the amygdala, all right? That backpack are the eyeballs. The eyeballs of the brain I'm in, right? So, what's right in front of me? What's the lobe right in front of me? Frontal lobe, right? Behind me is the visual lobe. To the side of me is the temporal lobe. And then like up there is parietal lobe, right? Okay, let's say I'm the amygdala again. All right? What's next to me right here? Temporal lobe. What is the temporal lobe all about? Hearing, yeah. Language. Balance, sure. Language, yes. Language. Hearing and language, all right? The balance is right on the, next to the temporal lobe on the supplementary motor area. So that's not, it's not incorrect, but I want to focus on the language, all right? The language. So we have two here. So I'm the amygdala, I have the language here, and then I have the frontal lobe right in front of me. So let's say I had a fear response. The brain has a fear response. Ah, what is happening? Two things.
Pardon the brief interruption. Freshmen with last names A through R. If you have not met with your counselor one-on-one to discuss scheduling next.
So, everybody here good? So, well, I have a fear response. I just got hit by a football player.
Last names S through.
Two things are going to happen. My brain is going to make a statement. Whoa, oh my gosh, that hurt. I had to send a signal over there. The second thing, the brain had to send a signal to the frontal lobe and say, you have to move your body now and you have to make a decision. And the third thing, we send the signal to the motor cortex. You have to brace yourself and prepare yourself for this hit, and you have to make sure that you don't get hurt. You see? So even though the signal came into one area of the brain, it ballooned out to three areas. Make sense? So this is called the global workspace theory of the brain. Which makes sense. Cool. I want to draw it up really quick. Wow, how do I keep losing this? So we have the first one, which is like floors, and then we have the next one. Kind of ballooning out like this, okay? Right. Here's the newer theory. This is called integrated information theory. Integrated information theory says, all right. We have a bunch of regions of the brain, and the regions are talking to each other, and they are talking to each other in these clusters and networks. Okay? So we have these regions of the brain, these circles, and they're interlinked with each other. All right? So if I have a region called the amygdala, let's go back to my amygdala center. And by the way, this one would be the left hemispheric amygdala, and that would be the right hemispheric amygdala. Whoa! But so I'm in the amygdala right now, right? And right in front of me is the frontal lobe, and then we have a region, the motor cortex is right there, and then we have the other amygdala, the hippocampus is like right there-ish, temporal lobe. So we're constantly dancing and and synchronizing with each other, all right? And I'm constantly communicating to all the subset areas as well. So this is more than just a ballooning effect. This is a branching effect, where I'm branching out my patterns over there, and then I'm branching out my patterns over there, and I'm branching out this way. So what is that mathematical geometry? We have to have a geometry to describe ballooning effects. And this way is through something called graphs and nodes, edges and nodes, where these distinct clusters and they're connected with each other. So they're saying awareness is even deeper. Awareness is actually nothing biological, but awareness is biological and mathematical. It's mathematical, right? Awareness is coming from a mathematical concept. All right? And then we have the last one before our fun game. I'm really interested to try out this game. It's also seated, so you don't have to stand up, but oh my gosh, it'll be really fun. All right? So, the last one, called predictive processing. So now we have, this is one of the key things about integrated information theory. We have the math of the brain. We have the structure, the math, the shape of the brain. And we have these dots and these nodes, and we're connected, right? But now we need the physics of the brain. How do these dots and nodes and edges, how do they talk to each other, and how do they grow, and how do they get smaller? So the way is that these nodes and edges are a constant cycle of predicting each other. Let's go back to our amygdala region. Right? I'm the amygdala. So if I'm the amygdala, my purpose is to send fear signals to the frontal lobe to make sure that it doesn't get into scary places. Because the brain doesn't want it to go to scary places, right? The brain wants to be in a safe place. Okay? So if my job is to keep the brain away from scary places, I need to be able to constantly predict when the brain is going to be in a scary place. You don't want to go to a haunted house or watch a scary movie and then say every time, oh, is this going to be scary, yes or no? You want to be able to predict it. I know this place is going to be scary. I know this is going to be good. I know this is going to be bad. You need to have prediction. You need to have certainty. So predictive processing says that the amygdala and these regions of the brain are communicating with each other, then updating who they are, the region of who they are relative to one another. So this is the basis of neuroplasticity. If the amygdala is very good at its job, and the regions surrounding it, and they constantly tell the brain, hey, I know where the fear areas are, and I know the fear events, and I know the fear people, and the fear memories. I know them very, very well. Okay? Then the amygdala could train the other areas to get larger, and the amygdala to quiet down. It trains the brain to change itself. Let's go to another region. Let's go to let's do the areas in the thalamus that control the eye movements. Lateral geniculate nucleus. All right? The purpose of this eye area is to send signals to the rest of the brain to say, okay, this is how the information is coming from the eyeballs before it's sent to the visual lobe. All right? So I'm constantly looking back to the visual lobe, looking in front of the eyes, visual lobe, eyes. I'm predicting, oh, this is what the eyes are going to see, and I'm sending it back real quick. And the visual cortex and the other areas of the brain are telling me information to update what I am. Now I'm synchronized with these other areas. Okay? Predictive processing gives breath and air to information theory. Information theories are these strict nodes and edges. Predictive processing says, I'm strict nodes and edges, and I move and dance with the other nodes and edges. Okay? And so this is the physics of awareness. So we have the math of awareness and the physics of awareness, and it's rooted into with the biology or the anatomy and biology of the brain. Happy? Wow! Okay. So we spoke about these hierarchies of the brain. Who here is taking chemistry or physics? Yep. Okay. So the highest region of the brain, the largest region of the brain are those networks, right? The tracts and the networks. Right underneath it are the neurons and kind of neuron groups, regions, neuron populations. The region underneath are subcellular, mitochondria, nucleus, endoplasmic reticulum. Inside are these different molecular components. All right? This is a dopamine, serotonin, amino acids, and proteins. And then those are built up upon atoms, right? So this hierarchy of the brain is super important to describe how information is flowing. Because at the end of the day, because everybody here learned today that awareness is based upon math and physics principles. So the awareness, Gavin and Mo, their deepest identity, the deepest self-awareness of who they are actually goes down all the way down to the atomic level. All right? So which region of the brain is Mo, so to speak? Which region of the brain is Gavin? To really get the correct answer, we have to go down to the atomic level. That's Gavin. Okay? So the largest and we have the smallest. Let's play a game. Let's play a guess. Which one do you think moves faster? A big neuron, that big tract of a brain, or the electron that zooms around the atom, nucleus super fast? Which one is moving faster? Electron's moving faster, right? This one doesn't spin around that fast. It moves slowly. Okay. So now we have it again. The larger areas are the slowest, and the smaller areas are the fastest. Information, self-awareness of who an individual is, moves faster at the atomic level and moves slower at the network level, right, regional level. Everybody here learn about action potentials, right? Action potential. Which, if you can, let's play a game. Good question. Which one of these is, where do the action potentials lie here? If you had to pick, where is it? Where do the action potentials lie? Neuropopulations, right? So, these action potentials, good. How do you activate an action potential? What does the pre-synapse need to do with the post-synapse? What does it need to send it? It needs to send neurotransmitters. Where's neurotransmitters? Molecular level, the dopamine. This is dopamine. All right? So the faster component of the brain, the dopamine, moves first, and then it goes up the hierarchy, and then the neurotransmitter action, the action potential of the neuron occurs. All right? Every single disease of the brain have abnormalities on how these hierarchies are synchronized on some form. Either either the slow regions are moving too slow and they're not connected, or there's a lack of specific neurotransmitters on the lower hierarchy. Every single disease, every single brain pathology is rooted around a dysfunction on one of these hierarchies. Okay. I have a question. We look here, this is easy. Easy peasy network neural molecular atomic. Who here could give me what's underneath atomic? There's one thing underneath atomic. What is it? Subatomic. You know what? That's a correct answer. That is correct answer. It is subatomic. But that's not the answer I'm looking for. So that's very funny. Okay, here, let's give it a hit. E equals mc squared. Einstein's E equals mc squared. All right? Does a proton have mass? Yeah, I mean, there's a little bit of mass, but there's mass. Does a neutron have mass? Does dopamine have mass? Okay. So E equals mc squared. Where is it? Is this going to be in the M region, the E region, the C region? Which one of these? Okay, is this M? This is M. This is M. Where's E? Where's E? You said M equals E. That's what Einstein said, the Einstein equation. What does that mean intuitively? M equals E equals mc squared. Who here could guess what E is? It is energy. Who can guess E? The physical manifestation of E. Yes, a photon, electromagnetic radiation, the electromagnetic field. This is super duper important. Our entire company, all our trials and the doctors are built upon this one concept. E equals mc squared. We only exist because of E equals mc squared. So we have a bunch of M's, dopamine, serotonin, GABA, right? Neurons, amygdala, big regions, M. Then we have also smaller M's. We have atoms, carbon, hydrogen, nitrogen, right? But there's one E. They all make up that electromagnetic field. Okay? We're going to touch upon these subjects later. But does this make sense? This is the basis of E equals mc squared. You have a big field of E, a big electromagnetic field. It's like a big fishing net. And out of the fishing net pops out these M's. Mitochondria, nucleus, brains, trees, atoms. They all come out of M. Does this make sense? That's the intuition behind E equals mc squared. Alrighty, isn't this so fun? Isn't it the most fun you ever had in your life? Alright. So we have these structures, network, neuron, subcellular, kind of these layers. Alright? And they're all dancing. Okay, they're all moving. Some are moving slower, some are moving faster. Back and forth, back and forth, back and forth. What we're seeing is that the brain operates like an orchestra with notes. And the viola, right? What happens when you're at a concert and the orchestra is out of tune? Music is, it's sloppy. You want them in tune. You want them synchronized, like a song. All right? So if the super fast regions in the back of the brain, the deepest part of the brain, are very unsynchronized with the slower, larger action potential regions, there's going to be dysfunction. There's going to be seizures, electrical abnormalities, epilepsy, different types of diseases of the brain. All right? So, who wants to play our game? I want to test this game out. So this is actually the first time we're ever going to play this game. It's a seated game. So we're going to break the classroom into our layers, the brain layers. This is going to be the brain layers. So this is going to be the fastest layer. What's the fastest layer? Who remembers? Atomic. Atoms, yeah. This is the slowest layer. What's the slowest layer? That word, radiator, right? So we're going to have the slowest and the fastest. All right? So the slowest, we're going to play a clapping game. I'm very curious how this is going to turn out. So let's do slow claps. It's going to be 1, 2, 1, 1. Can we do this whole row? So just this row, 1, 1. Okay, stop. Does everybody remember there are 2? Remember that this is yours. It's not. This one has a new signal. Let's go. 1, 2, 3. 1, 2, 3. 1, 2, 1, 2, 1, 2, 1, 2. Let's jump back here for a second. Everybody do yours. 1, 2, 3. And then yours is a little bit faster. 1, 2, 3. 1, 2, 3. All right. So you can stop. Let's do it fast here. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Oh, I don't. Let's see this. Remember your clap. Your clap. Not other row. Ready? Ready? Begin. Okay. That sounds synchronized. Sounds somewhat in tune. There's some phase overlaps. That's kind of cool. So what happens is if we have these different frequencies, that was fun. Where's my remote? Where's the remote? Okay. So we have the largest regions of the brain. These are slow. 1, 2, 3. 1, 2, 3. Middle regions of the brain. 1, 2, 3. 1, 2, 3. 1, 2, 3. And then the fastest regions, atomic level. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. This is the musical or harmonic composition of signal information processing in the brain. All right? When these, you see how these are in phase with one another? They're very ordered and they're very structured. Okay? Like an orchestra. The cello is playing low, slow notes while the violin is going da-da-da, allegro. When they're not in tune with each other, that's when these diseases occur. Parkinson's disease, major depressive disorder, Alzheimer's disease. Okay? Does this make sense? Okie dokie? All right, so I'm working on my own theory of the brain with the company. So I have my own theory. So this is it's based on this theory, but can I share? All righty. So my theory of the brain goes like this. So it's based upon this. So we have these frequencies in the brain. Some are super fast, some are slow, right? What is that geometric underpinning of these frequencies? Can you show me hold in your hand a fast electromagnetic photon. Show me it. Can you put it in your hand? Is it right there? Show me an infrared one. Ultraviolet. Yeah. It is still there. You're right. We just can't see it. One of the things is we can't hold on to that E. We can't necessarily put it in our hands. We can't touch it. It's not physical. There's no N. It's not an M, it's just an E. Okay? So, how do I describe the geometry of an E? Well, how do I describe a concept? How do I touch something that's touchless? All right? So, a theory that I'm working on, and this is serious. I don't know if you guys are, this is like super serious to me. This is like, I'm very emotionally, like, really in touch with this thing. I've been working on it for like 6 years. Okay. So this is a concept called self-intersecting planes of the universe. What? So, you guys know Einstein's relativity? Einstein, the big sheet. You hold a big bed sheet, right? And you throw a bowling ball in the middle. What's going to happen? The bed sheet's going to deform, right? Whoa. So it's like a hole. It's like a cave, right? So this is the universe. The universe is, you have a structure, you throw a bowling ball on it and it deforms, right? But there's something else. Something we have to remember. The bedsheet deforms one way, but if we look underneath, it deforms another way, right? So from one perspective, the bedsheet goes in and out, right? But from the other perspective, if we flip it around, it's up like a hill, right? The underside. So one of the things is to describe how the underside interacts with the upper side. And how does this all relate to inner awareness and frequencies and all this stuff? So, we have E equals M, right? So we have M here, all the matter up above, the dopamines and the neurons. Then we have E, the electromagnetic field, right? And then we have something called negative M, which is right underneath the E. It's below the mattress, or below the bed sheet. So we have the M's that are making the bed sheet, and then we have the other side of the bed sheet, which is negative M. Mathematically, this would be negative M, or negative mass. And so, we're not going to get deep into this, but the point here, this is perfect. Who here knows about dark matter? Have you guys heard it? Dark matter's everywhere. What's dark matter? It's negative M. It's underneath the electromagnetic field. All right? And it's constantly talking to normal M. All right? And the way it talks to normal M, positive M and negative M, is through the electromagnetic field, which is an intersection between the upper and the lower. The upper and the lower, the self-intersection plane. All right? Does this make sense? You know, I was in a class 2 weeks ago, and I had a feedback from one of the students. They said, "You talk to us like we're elementary students. We're not elementary students, we're AP Econ. We're AP Econ students." That's what they said to me. "You talk to us like you're an elementary student. Why are you talking to us?" The reason, so I think I'm talking like elementary today too. The reason being is because we have these advanced concepts, anatomy, biology, and physics. But what is the emotion behind the concept? There's a feeling behind the concept. And that feeling is elementary. So if you understand a concept to the point where you can feel it and sing and dance with it, it's just a fun elementary kid thing, then you can deeply understand that concept and you can deeply explain it. All right? So let's move past this. But the important part here is that the brain integrates information like an orchestra. Na, 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 na. They're all, the regions are talking to each other, and they're synchronized. Okie dokie. Oh my gosh, we have 20 minutes left. Let's read this together, everybody. Ready? Our brains are trees. Number 2. Our brains operate through networks, not regions. Last one. The brain integrates information like an orchestra. Okie dokie. We have one more special section I created for this AP class, and we're going to talk about it next, but not now. Right now, everybody has their laptop. Can they use their laptop? Yeah. Okay. Please go on this website. Oh, did I not link it? All right. One second, everybody. But in the meantime, go on this website, okay? I forgot to link it. And then go down to your educational section or educational outreach, something like that. All right, and we're going to click something called Science Survey. But don't click it now because I have to link the new survey that I created just for you. So give me like 3 seconds. No. Almost there. All right, I published it now, so let's check here. Let's go to this website. Okay, I think it's working. So go click on Science Survey right now. Oh, I give another presentation. I use the prior questions, but please fill this out as much as you can. All right, and then we're going to talk about the last AP section reading.
I would say here for half the lesson.
We actually had this presentation down once or twice.
Yeah, I know.
Oh, I think the reason being is I think you need to refresh your page too. That's why it's so long. So it's okay though. If you refresh your view the mod page, you'll get it now. Thank you for your patience. So we're going to talk about some fun stuff right now. Just try your best. just look up when you're done. Good. I would like for you guys, the last 9 minutes, to present this to just this class. So if you have your final questions, rounds of questions. Okay. Just start right here. That's great, like this is amazing. Okay. Let me start just so I can focus on time. We have 2 minutes left. But I'm going to talk about, we run a lot of clinical trials and we work with MRI machines. Anyone here's heard of MRIs? So the principle about MRI is that they use these big magnets to send some pulses, electromagnetic pulses, to shake up what's happening inside the brain As the brain is shaking and is shaking back to normal, they pick up on how it shakes back to normal. So if you think about it, you hit the tree is shaking, and then you're studying, how does the tree go from shaking back to standing still? So this is the concept of MRI machines. It uses frequency pulses to measure how the brain is structured and how it's functioning over time. More importantly though, many advanced new ways to study how the structures. So this is something called diffuser tensor imaging, which just studies how these white matter fibers are connected throughout the brain. Who here knows about the band Muse, M-U-S-E? Have you seen this before? So this is, they used a tractography, a diffusion tensor image on their album, if everybody saw this on the album. But this is a very important way. In fact, a lot of the science behind our company is based upon studying these tracks for the specific patients, because different patients have different tracks, and then sending the pulses along the tracks, the electric pulses. Alrighty? Coolly? Alright. Let's do the next one, which is a new type of way to handle. Is this mouse connected?
Yeah.
Okay. So this is called connectum harmonics. So remember how we talked about the brain has all of these frequencies and an orchestra, right? So this is a new way to use MRIs to look at the orchestra. This is the orchestra of the brain. All right? So the way to do it in summary, because I want to go to the last one, because the last one is, I love the last one. So the way that they do this is they have two regions of the brain. They pick up the shaking of the tree, so they have this branch and this branch, right? And then they use simple math, which describes, okay, this one's shaking like that, the other one's shaking like that. How do they shake together? And when they figure out how they shake together, that's when they can create this movie. Oh, this is how the brain is shaking in an instant. Okay, the harmonics of the brain. Okie dokie, let's go to the last one. Oh. So, this is, oh my gosh, this is such an important concept. So important. And who here is who's gonna study engineering in college? Math? Who is gonna study math or physics? Yeah, you're gonna do math or physics. Who wants here to go to medical school? Pre-med, nursing, stuff like this, healthcare? Awesome, cool. This is all important, all important. This is literally the coolest thing ever. This talks about, okay, we have 4 dimensions of the universe, right? 3 dimensions of time, 3 dimensions of space, 1 dimension of time, right? Topological data analysis says, are there any other hidden dimensions inside the brain? All right? Are there extra dimensions inside the brain of how these different regions talk to each other? Their answer is yes. The brain is a multi-dimensional system, and this entire universe is. But the brain can be mapped, and we can identify the images. So, for example, if I have 2 regions of the brain, let's do me again, this one and this one, and they're constantly talking to each other, right? Then but they're far away. One's all the way over there, the one's all the way over there, right? So they can't talk to each other instantly, but they can yell across the room, right? But it seems like they're dancing instantly. They seem like what the other one knows what the other one is doing instantly. How is this possible? The way in which this is possible is because these 2 regions are connected with a hidden dimension that we can't observe, called toruses. A torus. It's a hidden dimension that is in the background of time. It lies outside of time, and that's how they talk to each other. All right? And then we have other structures. So what happens when we have a region, these 2 regions in my hand, right? Region A and region B, we have 1 more minute left, and region C. And we realize region A and region B fire together, but every time they fire, that region fires next. So this doesn't fire instantly, it fires on a later level. But it fires faster than any tract or road could take it inside the brain. Then what we say is that there is projections happening inside the brain, such that the brain is going from a higher dimensional system, higher dimensional manifold, to a lower dimensional one. The point is, the really point is that the brain and all information is integrated outside of 4 dimensions, 5, 6, 7, 8 dimensions. And they're connected and they talk to each other. Hidden talk. So this is the last way to analyze the brain. All right? So we didn't have time today to talk about the physics of our company and the devices that you see there, but maybe you guys could see it in the future today. All right? Hopefully you guys start seeing this on YouTube real soon. This technology, all this. Is this fun? Everybody had fun today?
Yeah.
Whoa. Right? Yes. All right.